Welcome to our next video on condensed matter theory. In this video I want to discuss the Drude model and the basic assumptions that Drude makes in his model. So we basically introduce the model here, and then in the next videos we will have a look at different material properties that we can understand with the use of his model. And Drude, shortly after the electron was discovered by Thomson, used a kinetic gas theory for the electrons to describe the properties of materials. So he realized that you must have about 10 to the 23 electrons per cubic centimeter in a metal, and that you then can look at a statistical theory such as the kinetic gas theory to describe these properties. Now, using the kinetic gas theory that is derived for non-interacting gases, where you have much more volume per particle, in particles that weakly interact or only have point contact like interaction. For electrons, where we have of course strongly interacting particles that are close to each other, is quite a daring assumption to make. And actually neglecting that electrons interact with each other and neglecting that electrons interact with the nuclei that you have, whereby Drude, he didn't completely know the atomic structure, but he assumed that you have something like a nucleus, or maybe have something like a nucleus. But neglecting those interactions is actually quite ridiculous if you think about it. Nonetheless, it's very successful, and only in 1956 by Landau, Fermi liquid theory has gotten some basis on why this might happen. And you can derive this by diagrammatic perturbation theory, which we will actually do in next semester, where we have a look at Fermi liquids. But still, that is not an it must, it isn't showing it can. Good, then let's have a look at Drude's model. So we already assumed that we use the kinetic gas theory, so electrons move without any interaction until they collide. And we're going to say electrons don't collide on other electrons because they're so small, but electrons collide of nuclei. And Drude assumed this really to be the nuclei in a solid. What we know now is that electrons collide on the impurities in a crystal or on phonons. So if you have a perfect crystal, then we will show later on in the lecture that electrons actually do not collide, or the quasi-particles that we have, which is a better word, but we'll call them electrons, only collide on either impurities or on the phonons. So with temperatures, your atoms do not sit perfectly in a regular lattice, but they move about. And on these movements that break the periodicity of your crystal, electrons can scatter. So we have the Drude model, and in the Drude model the electrons move on straight lines until they collide, and they move in a different direction, and then they collide again and move in a different direction. Now, the assumptions or the ingredients that we have in our model is that between collisions electrons travel as free particles. The second assumption that we make is that collisions are instantaneously. So we don't have to say you slowly bend in a potential, you just move, at some point in time you collide, and then you move in a different direction. The third assumption that we're going to make is that we have an average time between two collisions. And this average time we're going to call tau. So your electron moves, then it scatters, it moves, it scatters, it moves, it scatters. The time can vary, but on average the time is tau. And the probability to scatter is constant in time. And the probability to scatter is then given by 1 over tau times the time interval. That will immediately give you this average time of tau in the scattering. So each point in time you have the same probability to scatter, and on average you have a time tau between your scattering events. Then we have a scattering event which changes the momentum of your electrons. And we say that a scattering event, the impulse after a collision, is randomly orientated and has a total moment such that the kinetic energy is given by what you would expect in the Maxwell equations for the kinetic gas law, 3/2 k T. So the electron, after a scattering event, doesn't know anything about the impulse or momentum that we had before the collision. If we say this collision happens at position 1, then we find here the impulse, the momentum, to be p squared over 2m is equal to 3/2 k T1, where this is the temperature at this point in space. We have a second collision, and the momentum that we have is p squared over 2m is such that p squared over 2m is 3/2 k T2. So that gives you a coupling between the temperature in your crystal, and temperature gradients in your crystal, and the momentum that we have, whereby the orientation can be random. These are all the ingredients that we need, together with basically Maxwell's equations, or the Coulomb law, if you put this in a potential to accelerate electrons. And then from that we can derive all the properties that you find within the Drude model. And some of them describe actually material properties really well, and even when we make the properties more and more realistic by including quantum mechanics, we'll still start out with quantum mechanics, and we'll still first assume that we have some collision time, or some time between two collisions, tau. And it's only later in this lecture, where we discuss randomness in a lattice, that we can actually derive tau as the imaginary part of the self-energy that we have for the electrons that propagate through that crystal. But that later in the lecture. For now, thank you very much, stay healthy, and we see each other later.